Hello all, welcome to the video lecture series for the subject operating system. Now I'm going to explain you all about a classical synchronization problem, that is dining philosopher problem, right? So the name displays like dining philosopher problem is a classical problem of synchronization, which says that five philosophers are sitting around a circular table and their job, that is each philosopher's job, is to think and eat alternatively. So you can check it, all those these, five philosophers are here. See here you can see that there is a circular table here. Assume that a bowl of noodle is placed in between over all the philosophers sitting over there. So here the center of the table, you can see that a bowl of noodles is placed, and the table along with the five chopsticks each of the philosopher will have adjacently. You can check that. Now to eat, a philosopher needs both the chopsticks. Say for example, a philosopher 0 wants to eat, so the philosopher 0 needs C0 and C1, that is chopsticks. C stands for chopsticks, P stands for philosopher, right? So here a philosopher can only eat if both left and right chopsticks of the philosopher is available. Say for example, philosopher 0 want to eat. That means the philosopher 0 basic requirement is, that is chopsticks number 0 and chopstick number 1 should be free. Only then this philosopher is active in taking these chopsticks for eating, right? So here you can check that in case of, say for example, in case of both the immediate left and right chopsticks, that is C0 and C1, I am pointing only P0 not, that is philosopher 0. If left and right chopstick, that we used to call it as adjacent chopsticks of philosopher, are not available. Say for example, C0 has been picked by P4 and C1 has been picked by P1. Say for example, it was not available, only then these chopsticks are not available, right? So then the philosopher put down either left or right chopstick and start thinking. Say for example, if P0 is having C1, for example, C1 is free, so P0 have took this C1, that is C1 is called as chopstick number 1. But P0 doesn't find this C0 is free. Why? Because P4 has been taken this chopstick already. So what this philosopher has to do, the basic idea is, if this philosopher want to eat, then both the chopsticks, that is left and right of this philosopher, should be available. If it is not available, this philosopher cannot process, that means they cannot eat with one chopstick. So what he will do, he will drop this chopstick and he will start thinking. So that is the process. So each philosopher need two stop chopsticks to eat. If they are finding only one, then again they need to drop that, then again they will keep on thinking, right? So this is the basic process of philosopher. Now the dining philosopher actually demonstrate a large class of concurrency control problem, right? So each and every process here cannot able to process at the same time. That means we are going to control the deadlock here, and hence it is a classical synchronization problem. That's why we classical synchronization problem. Let's get into the topic with basic example, right? So basically this automatically depends on semaphore. Say for example, I have drawn this particular units for philosopher, chopstick. Say for example, C0, C1, C2, C3 and C4. Now initially I have mentioned here the semaphore value is initially 1. That means 1 denotes 1 in the sense true, 0 in the sense false, right? So here all the chopsticks will be initially 1, 1, 1, 1, 1. That means all the chopsticks are available. Okay. If any of the philosopher is taking a chopstick, then this 1 will become 0. That identifies 0 tends to false. Means if any of the other philosopher want to take a chopstick, if it is not available, they will keep on thinking. Okay, so this is the prime idea about it. Let's get into the algorithm directly. Now you can check it. Semaphore will be initially 1. I already told you that. Here the algorithm starts. How does the philosopher, which philosopher is going to take the chopstick, who are allowed, and how this circular wait and circular pickup is actually happening. Now, do wait in the sense you all know that semaphore will have two function. One is wait, another one is signal. You can check it over here, right? Wait is to acquire, signal is to release. The same procedure we are going to use here. Okay, so let's see. Wait chopstick of I. Chopstick of I in the sense the I value will be initially C0. For example, it starts with C0. I already mentioned here, it starts with C0. Right. Now, assume that philosopher 0, say for example, philosopher 0 want to take chopstick. Okay, philosopher 0 want to take the chopstick. So chopstick of I, that is C0. You can check it here. Philosopher needs two chopstick, one is C0 and C1. So now philosopher checks that, and if chopstick of I, that is C0, is free, say for example what we have mentioned here, initially all the values will be 1. So if P0, that is philosopher 0, has taken this chopsticks, now what the 0 1 will become, it will become 0. I hope you understand how it is happening, right? Now the philosopher need two chopstick, right? So P0 will check the adjacent one. First, initially it will check the left hand side. If it is available, it will take it. And again, this philosopher needs one more chopstick, that is C1. This philosopher is not allowed to take C4, C3 and C2. Only the adjacent this philosopher can take it. So in order to model this circular process, the algorithm has been designed in that way. Say for example, wait, again I am going to acquire, that is philosopher 0 is going to acquire chopstick of I plus 1 percentile 5, that is modulus 5. What is this I plus 1? I is initially what? 0, right? And then plus 1. So I plus 1 in the sense 1. 1 modulus 5. You know very well what is the modulus value. If it is less than this higher value, then it gives the same. That is 1. That means I am going to pick up C1. So here you can check it actually. Process 0 already took this C0, and philosopher 0 will take this C1 now. So what is C1? It is going to check whether C1 is available. Yes, it is available. Why? Because the value of C1 is true. So when philosopher 0 took this chopstick, now C1 will become 0. So that will not be available. This C0, C1 and C0 will not be available for the other philosopher, which is very adjacent to this particular chopstick. So this is how the acquire is happening, right? So now let's see the same process when this procedure is true, that is both C0 and C1 is available, then this philosopher P0 will start eating. That is the process happening here. It will start eating, right? Say for example, if this philosopher is done eating, so what it will do, it will drop this chopstick in the same position where it has been taken. Now I am going to call this signal. What is the signal? Signal is to release, right? This is the semaphore function. We have already discussed in deep about what is wait and signal in semaphore. So again, signal chopstick. If I signal this chopstick of I, that means I is initially what? So I is called as C0. If I call the signal, this I will release this chopstick. Now what this C0 will happen? 0 will become again 1. Right? Again, this is the first one. 0 will become 1. So the final value is now 1. Right? Now again signal chopstick of I plus 1 modulus 5. So I is 0 plus 1 modulus 5. Again 1 modulus 5. That will become 1. So 1 indicates C1. Okay. So now we have a units here. So you can check it. So C1 will be released. So 0 will become again 1. This is step 1 and this is step 2. So finally we have, that is philosopher 0 has been taken and it is eating initially, and after that it is releasing this particular chopstick in the same thing. When the chopstick is released, what this P0 will do? Again he will go and think. Only two job, right? One is eating, another one is thinking. So here exactly we avoid when it is true. So finally we are going to close this. So when it is true, the same process will be keep on executing. Now you can check it. Only one philosopher is allowed to eat with the adjacent chopsticks, right? So now you can check it. If this P0 is eating, which two philosopher doesn't have a chance to eat? P4 and P1 cannot able to eat once if P1 has been picked this two chopstick. For example, if P1 is at the same time when P0 is eating, so P1 also wants to eat. Now P1 will check that C2 is available, that is chopstick 2 is available, but C1 is not available. Why? Because it is already took by P0. Again the adjacent philosopher here for this P0 is P4. Now P4 finds C4 is free, that is chopstick 4 is free, but it could not able to find chopstick number 0 because it is already picked by P0. That means if P0 is actually taking the process, that is philosopher 0 is eating, the adjacent philosopher has to wait. So here the possibility of the philosopher, that is at a time two philosophers can take, that means take a chopstick. Number 1 is P0 and number 2 is P3 or P2. Right? So this is how this dining philosopher problem has been designed in process synchronization solution. That is a process synchronization problem. This solution has been given for 5 different philosophers with 5 chopsticks. Thank you.